Casing is one of the most fundamental elements in drilling and well construction. From the moment a well is spudded until it is finally abandoned, casing plays a critical role in maintaining safety, integrity, and efficiency. A failure in casing design or selection can lead to serious well control issues, environmental damage, or complete loss of the well. In this video, we will take a detailed look at casing, starting with its functions, moving through the different types of casing, then covering steel properties, strength properties, specifications, and finally, casing connections. Let's begin with the functions of casing. The primary function of casing is to maintain the mechanical stability of the wellbore. As a well is drilled, the surrounding formations may be weak, fractured, or unconsolidated. Without casing, these formations could collapse into the wellbore, causing stuck pipe or loss of circulation. Casing provides structural support and keeps the hole open. Another key function of casing is zonal isolation. Different formations contain different fluids and pressures. Casing, combined with cement, isolates these zones and prevents fluid migration between them. This is especially important for protecting freshwater aquifers from contamination and preventing unwanted water or gas from entering the producing zone. Casing also plays a major role in well control. It provides pressure containment, allowing the well to safely withstand formation pressures during drilling, testing, and production. Surface casing, for example, enables the installation of the blowout preventer, which is essential for controlling kicks and preventing blowouts. In addition, casing provides a passage for future operations such as logging, perforation, completion, and production. It supports the wellhead and allows safe installation of tubing and other downhole equipment. Simply, casing is the backbone of the well. Now let's move on to the types of casing used in a typical well. The first casing string installed is usually the conductor casing. This casing is set at a shallow depth and is mainly used to stabilize loose surface soils and unconsolidated formations. It also provides initial support for the diverter, which is used to divert shallow gas kicks away from the rig site. Next is the surface casing. Surface casing is one of the most critical strings in the well because it protects freshwater zones. Regulations often specify the minimum depth of surface casing to ensure groundwater protection. Surface casing also provides the structural base for installing the blowout preventer, making it essential for well control. Below the surface casing, intermediate casing may be installed if required. Intermediate casing is used to isolate problem zones such as abnormal pressure formations, weak formations, salt sections, or loss zones. Not every well requires intermediate casing, but in complex wells, multiple intermediate strings may be needed. Finally, we have production casing or production liners. This casing is set across the reservoir and allows hydrocarbons to be produced safely to the surface. Production casing must withstand long-term exposure to pressure, temperature, and corrosive fluids, making its design especially important. Now let's talk about casing steel properties. Casing is manufactured from steel specifically designed for downhole environments. One of the most important properties is yield strength, which defines the stress level at which the steel begins to deform permanently. Once casing exceeds its yield point, it may not return to its original shape, which can compromise integrity. Ductility is also critical. Ductile steel can deform without cracking, which is essential during running operations, especially in deviated or horizontal wells. Toughness allows the casing to resist sudden impacts and brittle fracture, especially in low temperature or high stress conditions. Depending on the environment, casing steel may also need to resist corrosion from CO2, H2S, or saline formation fluids. In such cases, special alloy steels or corrosion-resistant grades are used. Next, let's dive deeper into casing strength properties. Casing strength is evaluated under three main loading conditions: collapse, burst, and tension. Collapse strength refers to the casing's ability to resist external pressure when internal pressure is low. This situation often occurs during cementing or when the casing is empty. Collapse failure can lead to severe deformation and loss of well integrity. Burst strength, on the other hand, measures the casing's resistance to internal pressure. High internal pressure can occur during pressure testing, production, and stimulation, or even a well control event. If burst strength is exceeded, the casing may rupture, leading to leaks or catastrophic failure. Tensile capacity refers to the casing's ability to support axial loads. These loads include the weight of the casing itself, drag forces in deviated wells, and additional loads during running and cementing. Tensile failure is a major risk in deep and extended reach wells. All these strength properties depend on factors such as casing diameter, wall thickness, steel grade, manufacturing quality, and safety factors used in design. Now let's move on to the casing specifications. Casing specifications define the physical and mechanical characteristics of the casing string. These include outside diameter, inside diameter, wall thickness, and weight per unit length. Weight is usually expressed in pounds per foot and is directly related to wall thickness. Steel grade is another critical specification. API grades such as J55, K55, N80, L80, and P110 represent increasing strength levels and different service conditions. For example, L80 is often used in corrosive environments, while P110 is used in high-pressure, high-load applications. Casing is also classified by length range, such as range 1, range 2, and range 3. Longer joints reduce the number of connections, which can improve running efficiency and reduce leak risk. Most modern operations prefer range 2 or range 3 casing. All these specifications are standardized under API 5CT, ensuring consistency, quality, and compatibility across the industry. Finally, let's discuss casing connections. Casing connections are just as important as the pipe body itself. They connect individual joints and must maintain mechanical strength and pressure integrity. The most common connections are API threaded and coupled connections, such as long-threaded coupling, LTC, short-threaded coupling, STC, and buttress threaded coupling, BTC. While API connections are widely used and cost-effective, they may not be suitable for high-pressure or high gas-oil ratio wells. In such cases, premium connections are used. Premium connections offer metal-to-metal seals, higher torque capacity, better fatigue resistance, and improved gas-tight sealing. The choice of connection depends on well depth, pressure, temperature, deviation, and operational loads. A weak connection can compromise the entire casing string, regardless of pipe quality. To conclude, casing is not just steel pipe placed in a hole. It is a carefully engineered system designed to support the wellbore, isolate formations, control pressure, and enable safe drilling and production. Understanding casing functions, types, steel properties, strength limits, specifications, and connections is essential for every drilling and petroleum professional. If you found this video useful, don't forget to like, subscribe, and share it with your drilling team. Let us know in the comments which oil and gas topic you would like to cover next. Thanks for watching.